In this video, we will discuss undecidable and intractable problems. First, let's discuss what an undecidable problem is. An undecidable problem is a decision problem for which it is known to be impossible to construct a single algorithm that always leads to a correct yes or no answer. An example of this is the emptiness problem, which states that a Turing machine E decides whether a given Turing machine M is empty. So, how do we prove its undecidability? We prove this by reducing the acceptance problem, which is said to be an undecidable problem, to an emptiness problem. Note that if the acceptance problem is reduced to the emptiness problem, and if the acceptance problem is undecidable, which it is, then the emptiness problem is also undecidable. So let's say we have an acceptance Turing machine A that decides whether a given Turing machine M accepts a string W. We then modify M to M prime such that it rejects all strings that are not W. So, the language of M prime can either be W if M accepts W or empty otherwise. So let's assume that the Turing machine E can decide whether a given Turing machine M is empty. We then run the Turing machine E on the input Turing machine M prime. If the language of M prime is empty, meaning M does not accept W, then the Turing machine E accepts. If the language of M prime is W, meaning M accepts W, then Turing machine E rejects. So basically, we can find out if E accepts a Turing machine M if we know whether that Turing machine M accepts string W, meaning we are using the acceptance problem to decide the emptiness problem. Since the acceptance problem is undecidable, it means that the emptiness problem is undecidable as well.
Thank you. This time we will discuss problems that are intractable. First, what is intractable problem? A problem is intractable if all algorithms, no matter how clever, will always run in at least exponential time. For intractability, we have subset sum problem. Given a set of non-negative integers and a value sum s, find out if there exists a subset whose sum is equal to the given sum s. For example, set A containing 4, 9, 2, 11, 5, and sum equal to 9. The output is true since there is a subset containing 9 and subset containing 4 and 5, which their sum is equal to 9. How to solve this problem? The most inefficient way to solve this problem is by using brute force. For example, set A containing 4, 2, 3, and sum is 5. First, we will create all subsets of the given set, then get the sum of each subset. The output is true because of subset containing 2 and 3. Its running time is big O of 2 raised to n and times n. 2 raised to n since there are 2 raised to n subsets of a given set, and n for getting the sum of each subset. It is very inefficient since it runs in exponential time. Another way to solve this problem is by using dynamic programming. Using the same example, we generate this table. The output is true because the rightmost cell at the bottom part of your table is true. So there exists a subset whose sum is equal to 5. To know how dynamic programming works, go to this link. Its running time is big O of s times n, s for the sum and n for the cardinality of the set. It is not efficient if the sum you want to find or the cardinality of your set is very, very large. However, it is not enough to show that subset sum is tractable. We will use gathering evidence to show it is intractable. One way to gather evidence that they are intractable is to find more and more problems for which we also don't know polynomial time algorithms and connect them to the problems that we know. Here is the chart of connected problems by Steve Cook and Dick Carr. All these problems have no polynomial time algorithm so far, and one of them is subset sum problem. So if we find a polynomial time algorithm for just one of them, All of them would be solvable in polynomial time. But nobody has yet found such an algorithm. That would be already a strong evidence that subset sum problem might be intractable. That's the end of the discussion. Thank you.